Today I am going to discuss on Francis turbine. You can see that this is the picture of a Francis turbine. Okay, it is named after J.B. Francis. He was an American engineer, and he designed a turbine which can work at different pressure heads. Okay, now in today I am going to discuss each and every point on Francis turbine and also the velocity diagram of the Francis turbine. Here, first, let me tell you the names of different parts. This is the volute casing. This outer casing, it is actually the covering of the turbine so that it prevents the turbine from any mechanical damage. This is the runner blades. This is the runner. That means the rotational part of the turbine. I am going to explain you. Don't worry. Guide vanes or blades. These are the guide vanes. Okay, this is the stationary part. It does not rotates. Here, it is the shaft. Shaft is mounted at the center. When the runner rotates, the shaft also rotates because the shaft is actually fixed in this way. You can consider that this pen is a shaft. This shaft is fixed, and when the runner rotates, the shaft rotates and it rotates the generator so that we get electricity. Okay, so water, this is water, this is the direction of water. You cannot see, I think. Now you can see it. Yes, this is the water, direction of water. Water enters through the penstock. This is the penstock. What is penstock? Penstock is a pipe of large diameters whose diameter is very large. Okay, you can see in this figure that from the reservoir where the water is stored at a great height, penstock brings that water to the turbine. Okay, so this is the function of the penstock. So water penstock brought the water to the turbine. Now where that water will grow actually. Now these are the guide vanes. You can see I have already told you that these are your guide vanes. What guide vanes does is that it does not have any rotational purpose. It is of not rotational purpose. It will not rotate, but it will guide the water to pass to the runner blades. Runner blades is inside. Okay, so it will guide the water. Suppose water is coming like this, it will guide the water so that water will enter from this portion of the guide vane and it may slowly move to the smoothly, I must say, not slowly but smoothly to the runner vanes. When it strikes the runner vanes, the runner blades rotate. Okay, suppose you don't use guide vanes, what will happen? Try to understand. Suppose you have got a turbine like this whose blades are attached like this. Okay, whose blades are attached like this. Now see, you don't have any guide vanes. Suppose this pen is the jet of water. So the jet of water directly strikes on the runner blades. What will happen? Runner blades will experience a severe shock. Due to that shock, the runner blades will not be able to rotate actually. It will rotate, but it will not be able to rotate at a very fast RPM. Okay, so your efficiency of the turbine will be very low. You won't be able to lit a lamp also with that speed. So if water suddenly gets into this runner blade, it will experience a jerk and it will not work. That's why we use guide blades, to prevent this jerk or shock. Okay, so when the water comes through these guide vanes very smoothly and it goes and strikes the runner blades. Okay, suppose I am taking this example that water is entering in between these guide vanes. This is one, this is the first guide vane, this is the second guide vane, for example. Okay, the water enters through this portion it goes on like this. The guide vanes are guiding the water to the runner vanes. Now it goes like this. It strikes the runner vanes like this. Okay, it strikes the runner vanes like this. The water which entered from here, in between the 2 and 3, it will strike like this. Suppose I've got suppose some part of the water has also moved up, isn't it? Suppose water is now entering from here. Actually, it has entered from all the parts. I am showing you examples. Suppose water has entered from here. Okay, what will happen? These guide vanes will guide the water to move to the runner vanes, and it will go and strike it like this, because water will go and like strike like this. Here, from here, water will go and strike like this. From here, water will go and strike like this. So you can see that how it is striking the runner vanes. Okay, when it strikes the runner vanes starts to rotate, isn't it? The runner vanes will start to rotate, and the runner's vanes will rotate in this direction. That is the anti-clockwise direction, because this will hit, it will rotate like this. Okay, so runner vanes is the rotor of the motor. Runner is the rotor of the turbine. Rotor means the part which rotates. We have got rotor in electric motors also. There is rotor, there is stator. Stator means which is the part which is stationary. Guide vanes, it is fixed. It will not move. It will just guide the water which will flow into the runner. Okay, so guide vanes is stator because it is stationary. Okay, you have got the concept of volute casing. In volute casing, it is of decreasing cross section so that the velocity increases. You have got the concept of runner. Runner, it is the part in which there are some blades which are known as runner blades. When water strikes the runner blades, they rotate the runner. Okay, when the runner rotates, shaft will also rotate. You have got the concept of guide vanes. What is guide vanes? It guides the water to the runner vanes. Okay, if it is not there, then the runner vanes will experience a shock and they would not have run at a high speed due to that shock. Okay, now only one thing is left to understand in this figure is the draft tube. What is draft tube? Have you ever wondered, a question may come to your mind that the water which is entering the turbine, it is going into the turbine. Where it is going then? Is it getting consumed? No, water is not getting consumed. Try to understand. Okay, if this my 4 fingers, you can see my 4 fingers, this is, you consider these as vanes or blades. This is one blade, this is another, and that's why these are the 4 blades. Okay, you consider that these are runner blades. Suppose water, you consider this pen as your water. Okay, this pen as your waters, these 2 pens as your water. Water will strike the runner blades and it will fall down. It will go into the runner blade and it will fall down. So you must have a pipe to hold the water. Suppose this is my pipe. Okay, suppose this is my vanes, and now the water which will fall through the gaps of the runner blade will fall into this pipe. Okay, this pipe will transmit the water to the tail race. You can see this figure. Okay, tail race. Tail race, it is the portion where water is deposited. Where water is deposited after coming out from turbine. It is the portion where the water is deposited after coming out from turbine. Okay, now I have talked about the pipe which transmits the water to the tail race. That pipe is actually known as draft tube. Okay, and the design of that draft tube or that pipe, it looks something like this. Okay, that means the pipe is of increasing cross section. Normally we see pipes of simple like this whose cross section at the inlet and the outlet is same. Okay, but we do not use these kind of pipes over here. We use these pipes whose cross section is gradually increasing. What will happen when the cross section gradually increases? Here your area increases, isn't it? If your area goes on increasing, we know that from our common concept and from equation of continuity that velocity will decrease. If area increases, velocity will decrease. Now velocity decreases means kinetic energy goes on decreasing. Where will that kinetic energy go? That kinetic energy will be converted into pressure head. Okay, that kinetic energy will be converted into pressure head. So instead of wasting my kinetic energy, simply I am using that kinetic energy to convert it into pressure head so that the water from the tail race can be taken to the height of the reservoir. Okay, have you got it? This is the function of the draft tube. That means draft tube is a pipe which is attached just below the runner blades. Okay, and the pipe is designed in such a way that its cross section gradually increases. Just this much, nothing more in the concept of the Francis turbine. Now we have to look into the vector diagram of the Francis turbine. I have just forgotten to say you that Francis turbine is also known as radial flow. It is a radial flow inward reaction turbine. Radial flow inward reaction turbine. Okay, why reaction turbine? Reaction turbines are those turbines where the turbines are dependent upon two factors. One is velocity and another is pressure. Here both the factors are important, pressure and velocity, because when the water at a high velocity from this portion reaches to the guide vanes, it strikes the guide vane, so velocity decreases a bit and pressure energy increases. So both factors comes into play. Now inward, why inward? Because you can see easily that water from outside, penstoke which is outside the turbine, water from outside is coming gradually inwards. It is going inside, isn't it? From the guide vanes, it is moving inner to the runner blades and even inner, and then it slowly goes to the draft tube. Okay, that's why it is called inward reaction turbine. Why radial flow turbine? Radial flow turbine because at the outlet, suppose this is my runner vane. Okay, please try to give focus in this matter. Suppose I am considering this runner blade. Okay, this is neat one. This is this runner blade. Water enters and strikes this runner blade like this. Now water moves along this blade and leaves this portion something like this. Okay, have you got it? If you have not noticed, please notice it once more. Water enters and strikes the blade here over here, and then it moves along the surface of the blade and it leaves the blade in this direction. This direction is what? This is radial direction. It is towards the radius. At the outlet, it does not have any tangential component. It has got only the radial component. It is towards the radius. It is along the radius. Have you got it? That's why it is known as radial flow reaction turbine. Okay. Now I will do what? I will show you the vector diagram. Okay, which you will need to solve problems of Francis turbine. Okay, suppose I will take this vein. Okay, suppose this vein I will draw. I will just magnify this vein. Okay, in this page I'm going to magnify this vein. Suppose this was my vein. Have you got it? This was my vein. Try to see it. This was my smaller vein. I have just magnified that vein over here. Okay, no problem, I think. Water enters like this. Have you got it? This is my velocity v1. Okay, this is my v1. This is u1. This is vr1. That means a resultant of v1 and u1. If I do break v1 into two components, I will get one radial component, that is vf1. Vf1 is the flow component or radial component. Okay, it is also known as flow velocity or radial velocity. Okay, vf1. This total one is what? It is vw1. What is vw1? It is the whirl component. Whirl component or tangential component at inlet. Okay, have you got it? What is u1? u1 was the speed, tangential speed of the runner blades. We have seen that the runner blades have got a rotary motion. So anything which has got a rotary motion, it has got angular speed, and with this relation v equals to omega r, can you see it? Yes, now you can see it. V equals to omega r. If I know my angular speed omega, which is actually 2 pi n by 60 into r, so I can find my velocity. Actually this is small u. This is my small u. Okay, this is my small u, which is actually the speed, tangential speed of runner blade. Okay, now what happens at the outlet? See, the water v1 which has entered with a velocity of v1, it will move like this. Okay, and it will have only the flow component. That means the perpendicular component I have said at v2. Okay, at the outlet the jet of water will not have any tangential component or the whirl component. There is no vw2 because it is a radial flow turbine. Because at the outlet the water flows radially towards the center. Okay, towards the center. Okay. This is the flow component at outlet. This is my flow component or velocity at outlet. Okay, so this is my u2. Have you got it? Then this is my vr2. vr2 is the relative velocity at the outlet. Have you got it? If I name these angles now, this is alpha, this is theta, whatever you name. Naming is not that important. You have to understand the concept. Why there is no vw2 at the outlet? Because there is no whirl component or the tangential component at the outlet. There is only v2, or the v2 is actually equals to vf2 in this case. v2 is actually equals to vf2 in this case because there is no tangential component, only there is the radial component. Have you got it? Now, what is the power delivered to the runner? Power delivered to runner. What is the power delivered to runner? I've already said it is rho q vw1 plus vw2 into U1 into U. Okay, I've said this in my previous lecture on Pelton-Wheel turbine. Okay, here there is no VW2 in case of Francis turbine. VW2 is actually equals to 0. So my formula becomes rho Q VW1U. Have you got it? What is hydraulic efficiency? Hydraulic efficiency, it's the runner power divided by the water power. What is my runner power? I have found out the power delivered to the runner. It is rho Q VW1 by U. No problem in this. Now what is water power? What is water power? Water power is the power with which the water is falling from the reservoir to the turbine via penstock. So at the reservoir, the water is having at reservoir, water is having a potential energy which is equals to mgh. Okay, H is the head of the water. Have you got it? That energy is transferred into kinetic energy actually. Have you got it? That energy is actually transferred into kinetic energy. That is mgh. I can also write this in the form of rho qgh. I can replace mass by rho into q, where q is discharge. So if I cut these things, so my formula becomes V u1 VW1U divided by GH, where H is the head of the waters. If you have understood this and the concept, then you will be able to solve any kind of problem in Francis turbine. Okay, and if you have any problem regarding understanding, you please leave a comment. I will try to help you out. Okay, thank you very much.